Have you ever hit print on your laptop and watched your document emerge from a machine across the room? To make that happen, a digital file has to navigate the physical space of your office network. But how does it actually know where to go? To find you on a network, your device gets a software-assigned name called an IP address. Think of this as a temporary label, like a name tag given to you by the office manager. It isn't part of the machine itself, it's just a name assigned to you while you're at work. On the left is that software name tag, the IP address. On the right is a totally different identifier called a MAC address. This is the hardware address hard-coded right into the device at the factory. If the IP address is your name tag, the MAC address is the exact physical desk where you sit. When data travels through your office, it looks for that software name tag. But when it arrives at the local network switch, it hits a roadblock. The switch doesn't know who John is. It only knows which physical desk number connects to which wire. You have the right name, but you don't know which physical front door that person is sitting behind. Without a way to translate that software-based name into a specific piece of physical hardware, local communication stops dead in its tracks. This is where the Address Resolution Protocol, or ARP, comes in. It's the invisible translator for your network, bridging the gap between name tags and physical desks. Imagine you need to hand a folder to John, but you don't know where he's sitting. You walk over to the office intercom and broadcast a question to everyone. Hey, which desk belongs to John? In this diagram, you can see how that works. The sender sends out a message that washes over every single connected device. This is an ARP request. It's essentially asking the whole room who owns this name tag. Most devices ignore the shout because it isn't meant for them. But the machine that actually owns that name tag shoots a message right back, saying, "That's me, and here is my hardware address." This reply isn't a loud shout to the whole office. It's a direct private message back to the sender. Through this simple call and response, ARP connects the software name to the physical hardware, allowing the document to finally find its destination. But there's a catch. If your computer had to use the intercom every time it sent a tiny piece of information, the office would be filled with constant deafening shouting. To stay quiet, devices use an ARP cache. You can see it in this table appearing next to the computer. It acts like a receptionist's personal notepad, stored right in the computer's memory. Before shouting over the intercom, the device checks its notepad. Once it gets an answer, it jots down the physical desk number next to the name tag, so it doesn't have to ask again for the next few minutes. Since people move desks or leave for the day, these notes eventually expire. After a set time, the record is erased to ensure the notepad stays accurate. This local notepad is what allows network traffic to be fast and silent, replacing constant shouting with quick internal checks. ARP was designed decades ago for small, friendly networks. Because of that, the protocol was built on total trust. It has no way to verify if the person answering the intercom is actually who they say they are. What happens if someone decides to lie over the intercom? When the sender broadcasts an ARP request, a hacker on the network hears it. The hacker's machine instantly fires back a reply, claiming to be the target. The sender believes the lie and overwrites its notepad. Private data immediately starts flowing straight to the hacker.